as I said, Copernicus did not publish his work. His work was publicized by his friend Rheticus. The interesting story about Rheticus is that, Martin Luther was, the head of the Reformation movement, and he in fact had started his own group around him. And Martin Luther, being a reformist, he heard about this Copernicus' system through word of mouth. Okay, that's all Copernicus did. He would talk to his mathematician counterparts about his system, never showed them anything written. And so the word about Copernicus' idea that the whole universe can be turned inside out reached Martin Luther. And Luther said, that contradicts the Bible. Because the Bible says, Joshua commanded the sun to stand still. So here you have this guy who starts a whole Reformation movement in religion, right? He contradicts the church, he contradicts authority. And then when it comes to Copernicus, he says, no, Copernicus, you cannot contradict the Bible. Okay? So he says to his minister, Rheticus, go to Copernicus, find out what he's talking about, and turn him around. Okay? Because he cannot be right. He cannot contradict the Bible. Okay? I don't want this thing to happen. Okay? He was up in Poland. So, so Martin Luther sent Rheticus to Copernicus, and Rheticus' mission was to stop Copernicus from spreading this heresy, okay? That the sun does not move, that the sun is the center of the universe. We are the center of the universe. We on Earth. God made us, okay, and made us at the center of the universe. And he gave us the power. So he gave us this special place. And here was this guy throwing us out of our special place and contradicting the Bible. So Rheticus read the stuff, okay, and he was quite convinced by these arguments that I just gave you. And he said to himself, this is really good stuff. And Copernicus, you should publish this. And Copernicus, no way, I don't want to get my head cut off, I don't want to get trial of the heretics like that. So Copernicus would not publish. And so what, so Copernicus wrote a small book called the Commentarius, okay? And in that he described his work. And that's the first time that Copernicus' work got published, okay? Of course, Copernicus was immediately, trounced. So what were the objections? Okay, the objections were that, as I said, like Martin Luther himself said, you're going against authority, you're going against the Bible, you're going against 2,000 years of knowledge, okay? And the answer Copernicus, of course, would have given is that science, of course, is the advancement of knowledge and understanding. Then, of course, the main problem was you're going against observation. If the Earth was going around the sun, then the birds would be left behind, okay? What's going to happen there? So Copernicus' answer, of course, would have been that if you use reason and insight, the birds are in the air, and the air is also moving along with the Earth, and so the birds follow the Earth around, okay? Now here's a very important objection that his counterparts came up with, and they said that if you have a spinning object, the spinning object, like a potter's wheel, breaks apart, You have this famous movie called Ghost, right, with Demi Moore and Patrick Swayze. Is that it? Is that Patrick Swayze? Right. And then they had this love scene, right? And she's spinning pottery, and he comes in from behind, and he grabs her, right? And she loses control and presses the wheel on the pottery, and the pottery starts to spin really fast, right? And so all of this pottery flies straight in their face and covers their bodies. And so this was the problem, that if the Earth is spinning like a pot, and people knew about pottery, of course, wouldn't the Earth break apart? Okay, the Earth would just break apart. And the answer was, Copernicus had no answer to this, except the fact that the Earth doesn't spin that fast. All right, that's the only explanation. And then finally, there was the old problem of Aristarchus. Why is there no parallax? Okay, so if the Earth is revolving around the sun, the angle between the stars will be different between summer and winter. And I've gone through this diagram before, that if these are the stars, then this angle is small when the Earth is here, but it's very big when the Earth is here in the summer and winter positions. And so there will be a different angle. But if the circle is bigger, then you'll see that the angle is relatively the same. Okay? So and the bigger you make the circle, the smaller the difference between these angles. And that would give you the answer of why you don't have parallax. The other question, of course, would be why the objects do not fall to the sun. You know, you take an object like this and it falls to the earth. Why doesn't it go to the sun? And that is a good question which only Newton could answer. We were talking about Copernicus's successes, right? So he came up with this nice system. Remember, he was driven to a large degree by the aesthetics, the desire to make the planetary system simple and elegant. And he did do that. He had 6 circles for the 6 planets and 1 circle for the moon. So he had 7 circles for 7 heavenly bodies, which was a nice match. And there was a nice symmetry about it in terms of everything was going in the same direction. All planets except the moon move around the sun. So it's not perfect symmetry, but the moon moves around the earth. And there was order and there was harmony. And all the planets moved in one direction. Okay. Now that, by the way, turns out to be an important fact about the planetary systems as to why all the planets move in the same direction. And it turns out also that, you know, these planets, just like the Earth rotates, the planets also rotate. And most of the planets rotate in the same direction as they revolve. Not all of them, but most of them. And that turns out also to be a nice clue about the origin of the solar system. But that came later. But Copernicus had a nice system which was unifying. However, okay, also it was quantitative. In other words, he had numbers for the sizes of these different orbits, and he had numbers for how long the planets took to go around the sun. And basically that was the time that the planets took to go around the whole zodiac. Okay? So if the Earth took 1 year to go around the sun exactly, then Venus took 0.62 years and Mercury took 0.24 years. And then these were the sizes of the different orbits. Now if Pythagoras were around, he would say, you know, there must be a musical relationship between these numbers. You know, so if you make a string this long and you make a string this long and you pluck them together, they will sound harmonious. You know, because there must be a reason why God chose these numbers. And this actually turned out to be the main driving force for the next guy that we'll talk about, Kepler. You know, he was looking for the mathematical pattern in these numbers. There is a mathematical pattern, right? And it's when I show it to you next time, it will just be amazing, right? All right. So Copernicus, of course, did not come up with the mathematical pattern. I don't even think he thought about it. Okay. So the problem was that even though Copernicus's picture was very satisfying, very elegant, it failed. Okay. And what do I mean by it failed? The 6 circles that he had did not agree accurately with the position of the planets for predictions for conjunctions. When will the 2 planets come together? It did not agree. In fact, Ptolemy's 80 circles, revised by Alfonso X and his crew, worked better. So here's the important principle about the progress of science, is that, you know, you can sit back and come up with a nicer model, but your model, you owe it for that new model to explain what the observations are to the same degree as the model that you're trying to replace it. So aesthetics are important, but they can't be the end all. Okay, they can certainly guide you, but the theory, whatever theory you come up with, must fit the facts. And Copernicus realized that this was true, that he did not fit the facts. Now it turned out that the reason that Copernicus's model did not fit the facts was because he was again sunk in this paradigm. You know, we talked about the paradigm. And you guys are all in a paradigm of the modern world of thinking anyway. Okay, so whatever field you choose, there's a certain paradigm of thinking. So Copernicus stuck to that paradigm, which was that the orbits must be circles around the sun. Okay, so even though he shifted the center from the Earth to the sun, he kept the planets moving in a uniform circle around the sun and moving at the constant speed around the sun. So many revolutions per year. So in order to make it fit, because Ptolemy's was better, so in order to make the Copernicus, the new model, fit, Copernicus started to add refinements. Okay? And what he then did was he's still stuck in the paradigm of circles, and so what he did was he added epicycles and eccentrics around the sun. So if you look at his picture back here, right? Oh goodness, I had to go. Yeah, if you look at his picture back here, he put a little epicycle on Venus, and he put a little epicycle on Mars, and a little epicycle on Jupiter in order to make it fit. So he did, in fact, turn out to be able to make his system work. Okay, by make his system, I mean for the motion of the planets around the sun. He could make it work, but he couldn't do it with 6 circles for 6 planets. He had needed 34 circles. Okay, so he was back to complexity. Because a lot of people say, at least that's less complex than Ptolemy's picture of 80 circles. However, he had sort of given up the whole idea of making it simple and elegant, and it was no longer simple and elegant. And so we say, okay, Ptolemy's ghost continued to haunt the universe. Okay, now as I told you last time, Copernicus did not actually publish his theories. It was his friend Rheticus who came and he published his theories. And there's a nice poem written by Alfred Noyes called the Torchbearers. This is actually a very nice poem about the history of astronomy, all the way from the Babylonians all the way to Herschel, who we'll talk about in a few lectures. So it says, I withheld my book for many a year, it's talking like as if he was Copernicus, until I clearly saw that this tremendous music could not drown the still supernal music of the soul. Let the soul take courage then, if its own thought be true. Not all the immensities of the little minds can ever quench its own celestial fire. No, this new night was needed, that the soul might conquer its own kingdom and arise to its full stature. So, in the face of death, I saw that I must speak the truth I knew. So finally, he gave permission to Rheticus to publish, yeah? And the story is that on his deathbed, he touched lovingly the first printing, the first edition of his book. Then he died. So, but as you know, he was trying to avoid this fate, right? Because if you challenge the Bible, you challenge the faith, and you start making trouble, and there were a lot of people making trouble. In fact, in the updates to the Copernican chapter, you know that there was one guy whose name was Giordano Bruno, who actually got a hold of Copernicus's idea and started preaching them. He was actually a preacher. And then this church told him to stop preaching, okay, these revolutionary ideas, because they were going against the church, they're going against the Bible, and Giordano would not listen, and he kept doing that, and he kept traveling from country to country in Europe and talking about Copernicus's system. In fact, he even talked about how Copernicus's system could be extended, namely that the universe is infinite and that there are other planets out there besides the planets of our solar system, and some of these planets may even be inhabited. So he's even thinking like, he was thinking about extraterrestrials and all that sort of stuff. Anyway, the church didn't like it. They brought him onto trial. The Inquisition tried him, found him guilty, and sentenced him to death. And what they did was when they had him attached to the stake, they first drove nails into his tongue and nailed his tongue shut against his jaw so he would not speak anymore. And then they set fire to him. Okay? So it wasn't enough. All right. So, however, despite the fact that the church did not like the system because it displaced the earth as being the center of the universe, they actually adopted Copernicus's new system of 34 circles to do the further calculations that they needed to make a very accurate, a better calendar than the Julian calendar. Okay, and I'll come back to the topic of why the Julian calendar needs to be corrected. I talked about it in the book. And so they convened this conference called the Gregorian. They had all these cardinals come together, and here they're talking about the motion of the sun in the zodiac constellations, and they try to figure out how to do all the calculations more accurately. And the main problem that they were trying to solve was the problem that the Julian calendar was based on the fact that a year is 365 and a quarter days. By the way, this was figured out by the Egyptians, okay? And when Julius Caesar conquered Egypt, he found this out from the Egyptian priests. And so he had the calendar corrected by incorporating this extra quarter days. It turns out, as I mentioned before, that this correction is still not complete, and that later on the Islamic astronomers determined that the correct length of the year would be this value. So now I want you to calculate, and maybe you did this already in section or for homework or something, but I want you to calculate how many years it would take for an error of 1 day to accumulate if you have this difference and you were using, if this was the correct length of the year and you were using this value here, how many years would have to pass before 1 day, like if you were using 365 and the correct length of the year was 365.25, then 4 years would have to pass before you need to make a 1 day correction. But if this is the correct answer instead of this, how many years would have to pass before you have to make a 1 day correction? Okay, so let's see what you guys said. Everybody said 100 years. I believe that's correct. So let's do the simple calculation. Okay, if you take this extra factor 365.25 and subtract 365.2422, 365 and 365 give you 0, and this difference is 0.0078, which is nearly 0.01, right? Which means in 10 and 100 years, this will give you an error of approximately 1 day. Now you notice that if every century, now this means that every century you must correct by 1 day, okay? But you notice that if you do this correction of 1 day by every century, you'll still go wrong. So the correct correction is you should do every century that's divisible by 4. Is that right? By 400, right. You should do every century that's divisible by 400 in order to do the next level of correction, so you get this 078, right? Thank you. All right. So now I will give you some updates to Copernicus's chapter. And the first update, of course, is what are the methods by which astronomers and physicists or scientists showed that the Earth actually rotates and revolves around the sun. Okay, so what are the methods? And so the first proof, really, for showing that the Earth rotates, the first visible proof that shows that the Earth rotates, was done by this guy, Foucault, who hung this long pendulum in the Church of Paris. So if you go to Paris, make sure you spend at least half a day visiting this church. Okay? But it's still there. The pendulum is still there, and you can see all the spindles are set on the floor. But what I want to show you here today is how Foucault got this idea. I mean, it's a pretty cool idea to suspend a pendulum and see that the plane of the pendulum is going to knock these spindles down around the circle as the Earth rotates.
So I'm at the Houston Museum of Natural Science in front of the Foucault pendulum.
So the way Foucault got this idea was, he was a practical man, and he was working in his machine shop, okay, on a lathe, okay, and he was machining this long rod of I don't know what it was, steel or something, and so in order to turn this rod, the lathe was turning. Yeah, you should watch this one here. You can see the lathe is turning, okay, and what he did was, accidentally, while the lathe was turning, he bumped the rod. Okay? So now I want you to watch what this rod does is if I bump it first without turning the lathe. Okay? So here's this rod, and let me turn it this way. So can everybody see the plane? Oh, really tight here. In fact, it's easier if I do it this way. Can you see the plane of oscillations of this pendulum? Okay. So everybody can see the plane, right? So now think, what will happen to this plane if, while the rod is oscillating, I turn the lathe? Will this plane spin, or will it not spin? So it takes some thought. However, Foucault just observed that it doesn't change. Okay, here, see, I'm going to rotate it like this while that goes up and down, okay? So here we go, up and down, and now I'm rotating. Oh, I'm not rotating, I'm cheating. Okay, let's try it again. See, while this is rotating, that plane is still going up and down. So now Foucault thinks, hey, what if I had a pendulum, and instead of going this way, I was going back and forth like this, and instead of attaching it to a drill, I attached it to the rotating Earth. Okay? So now this guy's plane is constant, but the Earth is rotating it underneath it. Okay? And so it should draw a circle underneath the plane of the pendulum, because the plane of the pendulum doesn't change. Okay? So here's the picture. Here's the pendulum hung up, and now it's oscillating in this plane. And as the Earth rotates, the plane of oscillation is the same, okay? And as the Earth rotates, you see that it marks a different path on the circle. And this is exactly a circle in the North Pole. Okay, slightly, you know, the number of hours that it'll take exactly 24 hours to go around in the North Pole. And as if you do it at different latitudes, you'll take a different number of hours. And the pendulum can then be calibrated to give you the right number of hours. So then he set up this great experiment in the church. It was a little bit ironic that he actually set it up in the church, you know, to say, hey, here's the proof that the Earth actually rotates. Yeah? Because the church was against this whole idea. And then the people gathered, and, you know, this became really big news. So that was the first proof that the Earth rotates. So the next question is, let's calculate Earth's revolution around the sun. So the time that the Earth takes to go around the sun is 365 days, right? Multiply that by 24 hours, right? So that's this many hours. And the Earth-Sun distance, which is actually called 1 astronomic unit, is that many kilometers. So the speed is, again, 2 pi r divided by t. And that turns out to be 1 times 10 to the 5 kilometers per hour, or 3 times 10 to the 4 meters per second. So you see, this is 100,000 kilometers per hour. So we are going much faster this way than we are spinning this way, okay? Now, it turns out that this guy, whose name was Bradley, just around the time of Newton, used this effect to actually show, use an effect of the fact that when you observe a star, that you have to tilt your telescope slightly to be able to observe the star properly, and the tilt of the telescope changes on whether you're moving in this direction or whether you're moving in this direction around the Earth. Now, so think of it this way. Light is coming from a star, okay? And think of the light like rain falling on your head, okay? So if you're standing still and the rain is just coming down straight, right? So your umbrella is straight. But now if you're running and you want to protect yourself from the rain, you have to tilt the umbrella so that the angle of the rain. So now think of a star above the North Pole, right? And the light like rain coming down. And you want to catch that light in your telescope tube. Okay? So if the Earth was still and that star were directly overhead, then you would no need to tilt the star. Okay? But if the Earth were moving, then you would need to tilt the star to catch the light. And you would need to change the tilt of the star depending on whether the Earth is going this way relative to the light, or whether the Earth is going this way relative to the light. Okay? So this effect is called aberration. And what he observed was the tilt of the telescope had to change between summer and winter by a certain number of degrees, or some certain fraction of a number of a degree. Okay? So he figured out what that fraction has to be. So first he said, let me guess the speed of light. So he is the first guy who actually guessed what the speed of light ought to be. I'm going to use the correct number. Okay? So he said, if the speed of light is 3 times 10 to the 8 meters per second, and if the speed of the Earth is 3 times 10 to the 4 meters per second, like I just calculated from the previous slide, then the tilt angle has got to be this ratio, and that will give me the tangent of this angle. Okay? So if you take that ratio, sorry, that's your tilt angle here, 3 times 10 to the 4 divided by 3, this is 3 times 10 to the 4, vertical by base. Okay? And you see how small this number is, right? When you do this division, you get 10 to the minus 4, and that is radians. Okay? Now you have to convert that radians to degrees. So you divide by 2 pi and multiply by 360. Okay? So when you do that, you get a certain number of degrees, but it turns out to be a fraction of a degree, because this is 10 to the minus 4. So then you multiply by 60 to get minutes, and then you multiply by 60 again to get arc seconds. So when I do that and multiply this by, convert this to degrees, then multiply by 60 and multiply by 60, I get 20 arc seconds. Okay? Now 20 arc seconds is an extremely small angle. But nevertheless, as you calculated before, it is still larger than the angle of parallax between two, for the furthest star. Okay? How far is the parallax angle of a nearby star due to the two different positions of the Earth in its orbit around the Sun? And the answer was nearly 1 arc second. And so the tilt of the telescope is more than that, and Bradley could measure it right away, way before, it was 100 years before the guy who measured this parallax angle. So Bradley accomplished two things. One is he proved that the Earth is actually moving, and second, he got an estimate for the speed of light. So he was one of the first guys who figured out the speed of light. All right.